minus 89 times 10 to the power 3 Pascal. Let me do it again. 14.829 power 6 minus. Okay. Right. So we have calculated our maximum stress. Okay, normal stress, minimum normal stress. And also we also have calculated our tau max. So if we were to ask to compute the factor of safety, okay, let's say I expand the question, you have to calculate the factor of safety. So you go to this table, okay, where's the table? Okay, we go to this table. I'm going to take this table now. Okay, so, and I will also mention what material that we're going to use. Okay, so I'm going to state down here, assuming using ASTM A709. So from here, you know that the stress yield will be equal to what? So ASTM 709, okay, is equal to 345. So therefore, the factor of safety will be equal to 345 times 10 to the power 6 divided by 29.747 times 10 to the power 6. Okay, so 345 power 6 divided by 29.747 power 6 is equal to 11.6. That is your factor of safety. So what you could advise, okay, maybe you will advise, once you know these values, you advise, hey, this high strength low alloy steel, it might be too expensive. Okay, it has high cost. And then maybe we can just use structural steel, right? Structural steel is 250. You're still going to have a very high factor of safety. So this is what real life engineering is all about. Okay, this is, I just show you in an actual form, right? If you were to be given a structure like this, right? How are you going to apply what you have learned to formulate the factor of safety? Or it can also be used to calculate what is the actual size of your beam that you actually need. Okay, and the important thing is this. Over here, you have loading in different direction. You know that in the testing over here, right, it's all testing in what? One direction, right? So how to relate a combined loading into an axial loading that is found, this is found in materials handbook. They only do axial loading. They don't do loading like what you have over here. Okay, so the only way to do this is to use what? Mohs circle to determine where you have zero shearing stress. Because when you have uniaxial tensile test over here, right, the shear is also equal to what? Zero. Again, this is true engineering work now. Okay, this is what a typical mechanical engineer has to do. Okay, so you can see in a nutshell, right, what we have done over the last 3 pages is to combine everything that we have learned, right? Drawing an element, determine our shearing stress, and finally calculate our factor of safety, actually knowing what this value actually means. Okay, then you can calculate the true value. If not, we are taking quite a big risk. Okay, right. So this is what is expected of you. If you were to ask me in a final exam, one question will be like that. Okay, where you have to combine all that you have learned into one question. Okay, now that's not all. The next thing, I like to do, I know I've done element B, okay? Now, sorry, element A. Let's consider element B, okay? Let's consider okay, element B. Now, element B will be quicker. Why element B will be quicker? Because for element B, right, the good news is this. For element B, remember we did an analysis. We know that one of the shear is equal to what? 0. Okay, is the shearing stress that will take the most time. The normal stress, as you can see, is pretty quick. Okay, okay, let's look at element B. So element B, right, again, you have stress Z for element B. So we know it's still minus Px over A. Then you have My over Iyy multiplied by X. And then you have your Mx over Ixx multiplied by Y. Okay, so if my we have to look at all those our analysis. So if we were to look at our analysis, okay, oh, good news, right? You can see why good news. So based on our analysis, the moment due to X, right, for element B is equal to 0. So you see that element B is exactly at the center is equal to 0. So moment about X, element B equal to 0. Oh, moment about X, element B. So we know down here that this is equal to 0. Make our life easy, okay? Then moment about Y, again, you go back over here, you look at moment about Y, element B is going to be what? In tensile, okay? So we know that this is going to be what? Positive. So from here, we only need to consider PZ over A. And then, yeah, okay. So I'm now going to hopefully take this table. Okay. And then I'll come over here. So just to, so we know that this will be equal to minus, oh, so bad of me. I'm going to copy this. Okay, just so I'm going to give you headache, right? So we know that this is equal to minus 100 times 10 to the power 3. And then divide by area, which is equal to 5310 times 10 to the power minus 6 plus moment about Y, 9600. Okay, 9600 divide by Iyy. So Iyy is 9.01. Okay. So next we need to know the X value, right? So the X value is this value. So the X value, okay. So the X direction is over here, right? So you need to know what is this value. So this is the thickness of the web. So the thickness of the web, right, is 72 or 7.2. Sorry, I do apologize, 7.2. So 7.2 times 10 to the power minus 6 divided by 2, minus 3. So 7.2 times 10 to the power minus 3, the whole thing divided by 2, right? So this is the thickness of the web. Yep, we are good to go. So from here, we can calculate that this will be equal to 100 power 3 divided by 5310 power minus 6 is equal to 18.832. Plus by 9600 divided by 9.01 power minus 6 times by 7.2 power minus 3 divided by 2 is equal to 3.836 times 10 to the power 6. Okay, let me do it again. 960 times by 7.2 power minus 3 divided by 2 divided by 9.01 power minus 6. Yep, 3.836. Okay, so the normal stress that we can see now. Let me move this out of the way. Is equal to minus 18.832 plus by 3.836 is equal to minus 14.996 times 10 to the power 6 Pascal. Okay, let me do it again. Minus 18.832 power 6 plus by 3.836 power 6. Yep, minus 14.996. Okay. So now we look at the shear. I hope I can put them right. So if we look at the shear now, so there's one shear direction is equal to 0. So we know that Vx will generate 0. So is the Vy. Okay, so it's the Vy that that is going to generate a force. Okay, a stress. Sorry. So this is our Vy. Okay, so we bring it over here. So I'm going to get rid of this. Right. So the area we have to consider is this area over here. And this area over here. Okay. So you have to, because that's where element B is. Right. So we know that if we were to look at, so the shearing stress, intersecting plane is Z. Okay. The direction is Y. So this is equal to Vy over Ixx Qx over T. And we know that Vy will be equal to what? Vy is equal to our 25, right? Vy is 25. 25 times 10 to the power 3 Newton. We also know our Ixx is equal to 40.9. And then the thickness, which is this thickness, is T W, the thickness T of the web is 7.2. Okay. Again, the first moment of area. So Qx is equal to Qx of our flange plus by Qx of our web. Okay. Okay. So Qx, so this is our width. This is our depth. Okay. So the width is our for the flange is our BF. Okay. So BF is equal to 0.166. Right? BF 0.16. And then the depth is your TF. Okay, so TF is 11.8 times 10 to the power minus 3. Then you have your Y bar, because QZ, if we look at QX, is equal to width, depth, Y bar, right? So we know that the vertical direction, this is our Y direction, right? So that will be equal to D divided by 2, 0.205 minus by 11.8 times 10 to the power minus 3 divided by 2. Okay, this is where you have to practice, you have to have confidence, and you have to be really, really careful. I up to today, sometimes I still make mistakes. Okay, so you have to be very cautious. So the width, check again. The width is 0.166. That's your BF. The depth is 11.8. Okay, 11.8 because that's the TF. 0.2205. So this is your 0.205 and then okay. So next we have to class our web now. So the web, the width is equal to 7.2 times 10 to the power minus 3. Then the depth is d divided by 2, okay, 0.205 divided by 2 minus, okay, minus by the thickness of the flange, which is equal to 11.8 times 10 to the power minus 3. And then the y bar is, the y bar is still the same, 0.205, divided by 2 minus by 11.8 times 10 to the power minus 3, and then this is multiplied by half. So to clarify the method, this is width, depth, this over here, it is your y bar. Okay, just to make the method clear, okay? So from here, you have to be very careful now. So 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166. So it's equal to 189.22